Yep. We are ready to go. Over to you, Alfredo.
All right. Thanks a lot. Hi, everyone. Thanks a lot for attending to my talk today. I'm tremendously excited to be here. And I would really like to thank the organizers for giving me the chance of talking at what I think is one of the best conferences each year. So I wanted to open my talk actually by showing this picture of what I believe it was the second hackathon of the Evidence Synthesis Hackathon. It took place in Canberra and I attended, and it kind of had a profound effect on a lot of the things that I implemented since then in my evidence synthesis. So let me introduce myself. I was once young and naive. I spent a lot of time chasing birds around in the field, trying to understand their behavior and their reproductive biology. I spent 4 years on an island trying to understand these little buggers here, the house sparrow. And one of the projects that I had during that time aimed at trying to replicate a textbook example in evolutionary ecology. I massively failed to replicate that textbook example, which took a lot of energy. And after going through all the process of sadness, frustration, not knowing what to do, I was lucky enough that in my co-supervising team for the PhD, there was one of the world experts in meta-analysis, Shinichi Nakagawa. And he suggested that we could perhaps do a meta-analysis. And in 2019, we published what it was my first ever meta-analysis, in which we challenged this textbook example and showed quite a good evidence of publication bias in this field. In 2019, which is also the year that I finished my PhD, serendipity again, there was a postdoc position to do meta-analysis in ecology and evolution, probably one of a kind. And I applied for it and I got it. I was lucky enough. And since then, well, later on, I attended the Evidence Synthesis Hackathon. Since then, a beautiful romance started between me and meta-analysis. So I reconverted into a meta-analyst, also a meta-researcher, and generally an open science advocate. And today what I want to do is to combine these three passions of mine and talk a little bit about how we can improve meta-analysis in the field of ecology and evolution, which is the that I've mostly done research on. So let me talk a little bit about this. Join me in this little trip, starting with defining what a meta-analysis is. So a meta-analysis is often preceded by a systematic literature review. By systematic, we mean comprehensive, we mean transparent, and generally we mean an objective and an unbiased representation of all the literature. And then the meta-analysis itself is simply a statistical tool that allows us to quantitatively combine this evidence. We often weight this evidence by the precision of each piece of evidence, which is largely related to the sample size used to generate that evidence. And I like to think of meta-analysis as having three main goals. The first goal would be to test the overall effects. This is perhaps the goal that most people have in mind when they start thinking about meta-analysis. And I would say that a lot of people overthink that step because it's not only about the overall effect itself, it's also about the generality of this effect, which is heavily challenged by how much heterogeneity between effect size you find. And sadly enough, despite that heterogeneity has a profound influence on how we should interpret meta-analytic results, is actually not that often reported, at least in ecology and evolution, and even less used for interpreting the results. Okay, so we've tested the overall effects. Now we've looked at heterogeneity, and we found a lot, at least in ecology and evolution, that's the case. The next step would be to try and understand this heterogeneity, or try and understand the patterns of the effects. This is something that we often do by running meta-regressions. Let me show you an example coming back to our sparrows in which we run a meta-regression to try and understand if whether the effect size was published or unpublished would explain some of the heterogeneity that we found in our meta-analysis. And indeed, as you can see here, it explained more than 40% of all this variability. So we've tested the overall effects. We know the generality of these overall effects. We've tried to understand patterns of effects by running meta-regressions. The last but not least goal of meta-analysis that I think is often quite neglected is that we can try to use meta-analysis to generate new hypotheses. By using this bird view of zooming out and looking at all the evidence around, we can generate hypotheses that would be very difficult to test at the primary study level. So just a brief example, I will present this meta-analysis later on again, but here I want to say that we basically tested a hypothesis that given how many levels of the factor we found data for, would have been very difficult to test at the primary study level, because it would have needed an experimental design, the 7 or 8 different treatment groups, something that at the primary study level is very difficult, but at the primary, at the analytic level, we can use this bird view to accomplish this and generate hypotheses. All right, so we do meta-analysis because we need them to integrate and summarize this overwhelming amount of scientific evidence that we are publishing each year. We're publishing more than 3 million scientific articles each year by now. The amount of meta-analysis themselves is also increasing, since the first meta-analysis around the 70s and in ecology and evolution around 90s, because we are dragging a little bit behind, the amount of meta-analysis that are published is increasing to the point that around 5 to 7% of scientific articles nowadays are meta-analysis. In ecology and evolution, we are still lagging behind. So we are around maybe 2% of all scientific articles in meta-analysis. But this plot is showing that they are gaining in importance. So this rate of increase in meta-analysis published each year in ecology and evolution is faster than that of scientific articles. Perhaps one of the reasons for why we use meta-analysis other than to integrate is because they are really powerful. So they may allow us to take, let's say, 5 small pieces of evidence that themselves might not tell us much about the hypothesis we are testing, but we might be able to use meta-analysis or meta-analytic models to increase our statistical power and have a better understanding of the answer to the hypothesis. They can help to resolve apparent conflicts between studies, and if they are done thoroughly, they can also guide future research. Let me show an example of a meta-analysis that we published recently. In this meta-analysis is trying to answer a question that was posed in the 90s. Question basically is from ecology and evolution, and the idea is that, or the hypothesis suggested was that females in birds, they are able to manipulate which hormones and how much of these hormones they deposit in the eggs. And these hormones would modify the behavior of their offspring so that the behavior of the offspring would better fit the environment where these offspring were going to live. What the mothers are trying to do there, according to this hypothesis, is to try and increase their reproductive success or their fitness. So we recently ran a meta-analysis, a systematic pre-registered systematic review and meta-analysis, where we try to really summarize all that has been published in the last 30 years on this topic, since the hypothesis was suggested. Our meta-analysis included 57 studies covering 19 bird species, and actually more than 400 effect sizes or pieces of evidence, if may. And with that, we could test the overall effects. Is there a relationship between how much hormones there are and the fitness or reproductive success of the offspring and the mothers? So the first thing that we found, this meta-analysis, is that the overall relationship between hormones and fitness proxies was pretty unclear. And actually, it did not matter on whether we separated by hormones. So the overall effect was generally unclear. And as you can probably see already from the figure, if we think about the generality of this effect, it's also low because we found high heterogeneity, meaning that these hormone effects, despite that we did not find an overall clear effect, this hormone effect seems to be context dependent. So the next step would be to try and understand the patterns of the effect, to try and understand if we know in which context the hypothesis is true versus it isn't. So we ran several meta-regressions to do that. And unfortunately, we did not explain much of the heterogeneity. We found a few interesting contexts that could explain why studies differ in whether they found support or not for the hypothesis, but not much at all. So the take-home message for this particular meta-analysis would be that the relationship between hormones and fitness, despite having more than 30 years of studies looking at this hypothesis, it's still unclear. It seems to be quite context dependent, and we don't know which context matter here so much. Another thing that we can provide by doing this exercise is that we can suggest things that future research could focus on. So we suggested that future studies should look at other species, because as you could see, it was only a few species, given that we have more than 10,000 bird species. They should focus also on looking at other geographical locations in case there is a bias there, other than the geographical bias that you can see, and more context. And perhaps the most important thing is that we need to understand the mechanisms by which females might be able to actively or not manipulate these hormones, eggs, because only by doing that, by focusing on the theory behind it, we can really propose clear hypothesis and prediction to really try to understand this topic. One thing though, so this is all good, super nice study where we learned a lot all together, combining a nice collaboration between people. But not all studies on this topic actually could be meta-analyzed. We encountered quite low reporting quality in this field. And in fact, complete data extraction was only possible for 29% of all the articles, scientific articles that we had found testing this hypothesis. So what we did, we contacted authors to try and save some of this missing data. And we got quite a lot of feedback. But still, at the end of the day, there were 25 potentially suitable articles that we had to exclude because we did not have enough information. Common issues related to missing sample sizes, variances, the methods not being really clear, some results reported simply as NS, non-statistically significant, without telling you much about the quantitative value of that relationship. And one that was particularly frustrating is that in some primary studies, they reported having found a statistically significant effect or not, but they would not tell you the direction of this effect, meaning that we could not really use it to summarize or to run our meta-analysis. This is nothing new. I guess most of you in the audience, if you've ever started doing a meta-analysis, you've gone through the frustration of realizing that there is a lot of data out there that we cannot use because it's not reported. And meta-analysts have got together to try and write guidelines to help researchers from primary studies better report their primary studies in a way that we meta-analysts can use them. But it seems that it might be a bit more complicated than we think it is, because we are still not reporting our primary studies in a way that they can be meta-analyzed in most cases. One potential solution to this is that on top of reporting things as transparently and as detailed as possible, you should always share your data. because we might be able to use the data to fill in all this missing information. A few years back in Ecology and Evolution, there was this suggestion, wonderful paper in which they demonstrated how to use open data sets to run a meta-analysis. So not only how to use open data, but to actually actively search for open data sets through repositories rather than searching for the papers. And they had a great example on how to do that, which is fantastic. We can also still perform a normal systematic review and meta-analysis in which we find the scientific articles that are testing the hypothesis of interest. And then what we do is to use the associated open data to fill in the gaps, to try and fight this selective reporting and ideally also publication bias. And I wanted to talk about an example in which we did that. So this is a meta-analysis, a systematic review and meta-analysis, also pre-registered that we published a few years ago. In short, what we were trying to understand is whether differences in size, in body size between males in this fish are associated with the reproductive success. The idea would be that the larger you are, the more you reproduce. So we tested the overall effect after having performed the systematic review. And this is what we found. So overall, there seems to be support to the idea that the larger you are, the more you reproduce if you're a fish. And what you can also see from this plot by the prediction intervals that are depicted there is that despite that we found a clear overall effect, there was a high heterogeneity, which we tried to explain by running several meta-regressions. And what I wanted to use this example for is to showcase how we can use open data, try and mitigate the effect of publication bias here. So what I would like to first show you is the results of a publication bias test, specifically a small study effect, which we are trying to understand if there is evidence for these small study effects. And for this data set, or this meta-analytic data set is based on typical traditional meta-analysis in which you've gone to the papers you found through your systematic review and you've extracted what is reported in the papers, transform everything into a common currency or effect size, then test for publication bias. So this is what the publication bias test in this case would have looked like if we would have only used the results that were reported in the original scientific articles that we found. So what you can see here is that there seemed to be good evidence of small study effects, meaning in this case that the larger the sample size of the effect size or the study, the less evidence for the hypothesis there is, which is not something you ideally like to find. But what we did here is we not only used what was reported in the papers, but we designed our search so that we would find studies that would have the potential to test the relationship between male size and reproductive success. And we searched for those that had open data so that we could ourselves estimate this relationship between male body size and reproductive success. The first thing is that we, of course, found a lot of new data that we would have missed if we would have focused on the traditional way of performing a systematic review meta-analysis. And the next thing, and the thing that I wanted to highlight, is by doing that, we also mitigated the effect of publication bias on our results. As you can see in the second plot, there is also a tendency for the overall evidence for the hypothesis to decline as sample size increases, but that tendency was much more ameliorated. If I'm going to use a commercial break here, I wanted to say that if you're interested in learning a little bit more about how to test and adjust for publication bias, We ran a workshop 2 years ago in the last ESMARConf, and I also wanted to take advantage to say that the YouTube channel of the SmartConf is fantastic. There are so many resources that almost anything you need will be there. So go and check it out, please. All right, back from the commercial break. Hopefully, well, what I'm trying to do is to convince you that I think the future is open data. And I want to show you a little bit more evidence for why I think it is time for us to embrace this open data in our meta-analysis. And for that, I need to first define what meta-research is, which I introduced at the beginning of my talk, and to tell you what the difference between meta-research and meta-analysis is. So meta-research is basically the science of science. In meta-research, we are trying to study how we do research. So we might be looking at methods, reporting, reproducibility of a wide range of scientific articles, with the main goal of trying to understand what makes research reliable and to suggest things in which we can improve that. So meta-research is the research on research or science of science, whereas meta-analysis, remember that we said, is simply a statistical tool that we use to quantitatively summarize information. Okay, so with that little definition, we can jump into why I think the future is now for meta-analysis of open data. Here are the results of two meta-research studies that we've done in the last few years, in which we focus on ecology journals with sharing policies and without sharing policies. And long story short, what I'm trying to show you is that the potential for us to use or to run this meta-analysis of open data is increasing, because regardless of policy, the amount of code and data is increasing, meaning that this potential is also increasing. And not only that, it seems that across in ecology and evolution, the community is embracing open data more and more. So this is a survey that we did for 275 journals in ecology and evolution. And we found that the amount of journals that implement policies for data and code sharing are also increasing over time. So hopefully that is enough to at least inspire you to consider this meta-analysis of open data. And let me get back to meta-analyses are powerful. So remember, we said that meta-analyses are powerful because they might allow us to, among other things, increase the statistical power of our test, so to say. But the truth is that they are only powerful if they're done properly. And unfortunately, and you know what's coming, poor quality, it's kind of the norm. So I'm gonna try to convince you that that's the case by using a few meta-research studies in ecology and evolution. The first one is this study that was published in 2014, in which the authors looked at more than 300 meta-analyses published in the field of plant ecology, and they looked at methodological and reporting quality of this meta-analysis. They had a rating score that went from 0 to 14. The first thing that you can see here is that the reporting score is far from ideal. So not a single meta-analysis reached a value or a score of 13 or more. And in fact, on average, they were below 7. And also, there seemed to be little improvement over time, which I found quite surprising, particularly because in 2009, it was an important year for systematic reviews and meta-analysis across fields, because it was when the PRISMA guidelines were published. The PRISMA referred to the preferred reporting items for systematic reviews and meta-analysis, which, as you can see, has gained a lot of traction over the years. And I just wanted to say that this PRISMA is about reporting. It's not necessarily about how to conduct the systematic reviews and meta-analysis, but it can help because it makes you aware of what you should be reporting. So it will make you think about it. I believe these type of misunderstandings and more are going to be covered later on in the keynote by Julian at which I'm very much looking forward to. Prisma guidelines exist, or Prisma extensions have been published for different fields, including the field of ecology and evolution. So in ecology and evolution, the team of O'Day et al. Suggested the extension in 2021, specific for ecology and evolution. And I wanted to show, by using a data set that was compiled as part of that article, and an additional data set that we compiled, that despite that we've known about Prisma and other reporting guidelines for a long time, in ecology and evolution, most studies don't even reference these guidelines. What we don't know clearly is whether there is simply a lack of awareness, or whether maybe the authors do not know that they should be reporting. But there seems to be some evidence that meta-analyses that reference a guideline tend to have a higher reporting quality, or estimated reporting quality. So it is important that we spread the word, so that it is not really lack of awareness was keeping meta-analysts in ecology and evolution from using these guidelines. Okay, so we need better reporting in meta-analysis. I hope I made the case that we are suffering from similar problems as we've been complaining regarding primary studies. And here is the commercial, the commercial number 2. If you are interested in getting your hands dirty and doing a little bit of meta research together to understand reporting in meta-analysis, in ecology evolution, and also to understand common misunderstandings with effect size calculations, please join us this Friday at 10:30 a.m. And we would be running a hackathon in which we are trying to together do a meta-research project in which we evaluate these things in a pack of meta-analysis published in Ecology and Evolution. All right, back from the commercial break. So far, I've been talking a lot about reporting, but we need to understand that reporting per se doesn't mean reliability. They are different terms. We could, for example, think of reproducibility instead. And here I wanted to show the results of a nice study that was published last year, in which the authors tried to computationally reproduce the results of 177 meta-analyses published in Ecology and Evolution. The first barrier that they encountered was that only 15% of all these meta-analyses shared the data and the code. So it was that subset, the only one that could be attempted to be computationally reproduced. And then when they actually did the test, computationally reproducibility ranged between 35 to 18% in the most generous case. So computationally reproducibility in meta-analysis, in ecology and evolution at least, is quite low. In psychology, they've gone a little bit farther, deeper, and not only looked at the computational reproducibility of the meta-analysis, because basically you use the same data used by the meta-analysis and the same methods, and try to see if you get the same numerical results or very similar. In this study, what they did is that they tried to understand if the calculation of the effects per se would be reproducible. And as you can imagine, this has strong consequences for how much we can trust the results of the eventual meta-analysis. And to me, this actually was quite shocking that only 45% of the effect sizes were deemed or reproducible, or the calculation of these effect sizes. Maybe it's not all bad news, actually. So there is a recent paper led by Pietro et al. That seems to suggest that actually we might not be doing that bad, at least for this specific meta-analysis of meta-analysis, where they analyze more than 40 meta-analyses in sexual signals, which I very much recommend reading. All right, but again, I've talked about reporting. I said it's not is different to reliability. Computational reproducibility is also different from reliability. There are more things that would make the results of meta-analysis or not reliable. One question is what we are meta-analyzing even reliable, or said differently? Are the primary studies that we are including in our meta-analytic data set reliable themselves? We suspect they are not all reliable, but oftentimes we are treating them as equal. For example, the primary studies themselves might not be reproducible. These are two studies looking at reproducibility in primary studies in ecology and evolution generally, and reproducibility was deemed to be between 68 and 81%, and that's only for the studies, the primary studies that they could actually be tested, which is less than a quarter of all studies. The main barrier, as usually, is not having access to the data, even if you contact the original authors. A lot of data gets lost over time. But again, computational reproducibility is not reliability. We might still amplify these effects by meta-analyzing primary studies that are unreliable themselves. One important thing to consider when we are doing a meta-analysis on primary studies is whether the studies, the evidence that you are extracting from them, whether this evidence actually can establish a causal relationship between the two variables that you are interested in, and a causal relationship that is free from confounding factors. This can be actually quite tricky. What we need to understand better is the internal validity of these primary studies. This internal validity can be challenged by multiple biases in data collection, in the analysis, and the result interpretation, in the type of experimental design that is used, etc. And this is something that pertains the risk of bias assessments, which, as I'm going to show in a little bit, is pretty much non-existent in ecology and evolution. In medicine, risk of bias assessments seems to be quite common. So some estimates suggest that they are almost done every time, which I guess it's possibly not applicable to all studies, but it's very positive. And the implementation of risk of bias assessments is increasing over time, apparently. In ecology and evolution, we had an estimate from a few years back in which it was deemed that only 4% of all systematic reviews in ecology perform some sort of risk of bias assessment. And why is it? Why aren't we doing this risk of bias assessments if they are so important to understand the reliability of the meta-analytic results or the systematic review results? So this is to try and understand this, we got together in a project brilliantly led by TITSA, in which we survey ecologists and evolutionary biologists that had some experience doing meta-analysis and systematic reviews. And we asked them a few questions. The first question is if they had heard about risk of bias or risk bias assessment. And around 50% said that they had heard of it. However, when we ask a little bit further, what we realize is that only 12% actually knew exactly what risk of bias assessment is. Many of them were confusing it with publication bias, which is slightly different. And from all the ecologists and evolutionary biologists that had performed a meta-analysis or more, only 4% declared to have conducted a risk of bias assessment. And those that had performed one, they thought it was actually quite difficult to do, which might explain why risk of bias assessment is not common in ecology and evolution. By the way, this 4% was surprisingly close to the 4% of the previous survey, despite being a rather different approach to estimating this rate. All right, so it seems that ecologists and evolutionary biologists do not know what a risk of bias assessment is. And those that had done it actually thought it was very difficult. So One possibility is that it is so difficult, a lot of people have decided not to even attempt it. And in this new contribution brilliantly led by Antitza, we are suggesting a simple yet powerful way of at least starting thinking about risk of bias in ecology and evolution. And here is commercial break number 3. If you want to hear more about it, I recommend you join the workshop that Antitza is running tomorrow, which I can't wait for. All right, let me finish up with a few take-home messages. I hope I've convinced you about my passion regarding meta-analysis. I really think meta-analyses are tremendously powerful, but they are only so when they are done appropriately. And this is something we always need to consider. Issues from primary studies apply to meta-analysis too, despite that we as meta-analysts have been complaining a lot about reporting quality in primary studies. We are kind of doing the same meta-analysis too. These issues actually could be amplified because we might be using unreliable primary studies to generate unreliable meta-analytic estimates. And we should consider how we can better account for these potential errors. I hope I've convinced you that open science is an option. It's really foundational. We really need to embrace it more and more. And a way of potentially embracing it in meta-analysis is by incorporating open data into our meta-analysis. Last but not least, I wanted to showcase how we can use meta-research, the research on research, to try and understand what we are doing wrong or suboptimally and what we can better. And with that, I would like to finish my talk. Thank you all for your attention. Thank you again for the ESMARConf, one of the best conferences each year. And I'm really looking forward to having some of your questions now. Thanks.
Thank you, Alfredo. We have a few minutes for questions. Questions can be asked using the Q&A in Zoom for Zoom participants or in the chat on YouTube.
Should I read them from the chat, or would you do that for me?
I will do that for you. We don't have any questions currently, so I will start off and ask what is, in your opinion, is the worst case of reporting you have seen? This might be a controversial question. You don't have to give specific examples.
Do you mean reporting in primary studies or in analysis?
In meta-analysis.
I mean, something that really gets under my skin is when heterogeneity is not even reported. And that's quite often. I think that's extremely problematic for the interpretation of the results. I would say that's, yeah, something quite strong. Another thing that I find quite difficult to deal with is when it is unclear whether the authors have thought about the direction of the effects they are meta-analyzing, and when you start hesitating if it has been accounted for. Because if it hasn't, results can cancel each other. And we have found a few examples of those with the published open data from meta-analysis in which that has to be the case. And that's extremely problematic. Generally, what I would suggest is really to have a look at the Prisma checklist whenever you are reporting a meta-analysis and try to check as many boxes as your study allows, because everything is there. It's just maybe a little bit overwhelming, but everything is there.
Thank you. I'm just checking. We don't have any other questions currently, but please do ask any questions. Oh, we've just got one in. Is the reluctance to adopt risk of bias assessment in ecology due to it being hard, or because it will likely conclude that most studies are high risk of bias? That's Matt Lloyd-Jones.
Hi, Matt. I don't think the reluctance to not perform the risk of bias assessment is based on us thinking that most studies are not going to pass it. I really think people are unaware. And I think one of the barriers is definitely how difficult it is to think about this and perform it. Like in ecology and evolution, I think we have such a wide variety of study designs that sometimes, even when we get together, a few of us from different fields and discuss about how to test these risk of bias assessments or how to perform them, we find it quite hard to have this an agreement. So I agree with you. We probably find that actually a lot of the studies are under risk of bias, but I don't think we know that yet.
Thank you. We've got a question from Kate. She says, a great talk. Any thoughts about how trainees can learn/be taught to do high quality meta-analysis when many of the published MAs have flaws?
Well, that's always a difficult question. I have to say, I have 10 years of experience, 8 years of experience of meta-analysis, and I'm still learning. In every collaboration I have, I'm still learning. So I think exactly there is a lot of things to learn. But what I would recommend is that rather than relying on meta-analyses that are published and use them as templates for your own meta-analysis, I think you might want to check out some of the amazing handbooks and workshops that are available each year, in which all these things are covered, even if they may feel overwhelming. So I would try not to use meta-analyses that are published as templates, but look at the sources instead.
Thank you. We've got a point from Matt who says, I think this relates to the extent to which we should adapt risk of bias tools to the field or use them as motivation for improving study design/reporting in ecology. And we've got a question in the chat, which are what statistical skills do we need to have to do meta-analysis?
It's basically what I found most difficult with the statistical knowledge that you need to have for a meta-analysis is that oftentimes what you need to have is the very basic knowledge in statistics, which is not what we are taught to start with. So I really think you have to go back to the base and think about what a normal t-test, an ANOVA, a regression is, and try and understand those very basic concepts that we often pass them very quickly. And knowing those basics will allow you to really understand much better how to extract the effect sizes from the papers, which I think is the strongest limitation for doing a meta-analysis, because the actual meta-analytic analysis or statistical models, I think it's something you can learn much more quickly by attending some of the workshops out there, for example, run by Wolfgang Witzbauer or Shinichi Nakagawa.
Thank you. Speaking of Wolfgang, Wolfgang has a question. How do you think the field of ecology and evolution differs from other fields, in particular medicine and psychology, in terms of challenges when doing systematic reviews/meta-analysis?
Well, I think I can think of 3 quick differences or things that I think are different. Certainly in ecology and evolution, one thing that makes it very different to psychology and medicine is the fact that we are dealing in most meta-analysis with we are dealing with multiple species, which generates a lot of variability, and it generates a lot of complexity because we have to account for this phylogenetic relationship between species. The second thing that I think is quite different from other fields is that the amount of heterogeneity that we observe across ecology, evolutionary biology studies is very, very high, to the point that it's almost impossible to have a meta-analysis with a high generalizability or generality. And most of the time, you have a lot of things that you don't know, basically. And I think in some scenarios, particularly in medicine, that can be really restricted. And the last thing is really the wide variety of experimental designs that sometimes we use in ecology, and the fact that many of the experiments cannot be they cannot really establish a perfectly causal relationship, basically. Those would be the three things that would come to mind.
Well, thank you very much, Alfredo. That's all we have time for now, and thank you for everyone who attended.
Thanks a lot. Thank you for giving me the chance. I'm looking forward to the rest of the talks. Thanks. Ciao, everybody.